Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. So students, today we are going to discuss about the module Key Applications and Devices from the paper Functional Materials. The purpose of this module is to make the students familiar with the following. First, the applications of piezoelectric materials. Second, that is in the piezoelectric energy harvesters. Third, in sensors, actuators and motors. Fourth, in transducers, and the various applications like MEMS and dampers have been discussed. So students, let us start with a basic introduction about the module. The piezoelectric materials, they have a very wide scope as far as its applications are concerned. The electromechanical relationship that is established by piezoelectricity has been used widely in the development of sensors, actuators, dampers, photostrictors, micromotors, transformers, etc. These materials plays a very vital role in our everyday life. We are completely surrounded by the devices made of these materials. Piezoelectric materials are used in our cars, gas lighters, parking area, cameras, mobile phones, vibrators, accelerometers, gyroscopes, etc. So here we will be dealing with the following applications of piezoelectric materials. First, piezoelectric energy harvesters. Second, sensors. Third, actuators. Fourth, piezoelectric motors. Fifth, transducers. And lastly, various other devices. Piezoelectric energy harvesters. Since the last 3 decades, energy harvesting has been a topic of interest. The reason being over-exploitation of non-renewable energy resources and ever-increasing demand for energy. Energy harvesting refers to the process by which energy is trapped from the external sources and utilized directly to run the machines, or it can be stored for future use. Solar farms, wind farms, tidal energy utilizing farms are some traditional energy harvesting techniques. An excellent commercial example of energy harvesting is the recent system which is being developed by Perpetuum, which converts the vibration of rolling stock into electrical power for the wireless communication of sensors that predict the failure of rail wheel bearings. The ability to deliver sustainable power to a wireless system network by energy harvesting is attractive not only because of the cost of batteries, it also removes the additional time and cost that is necessary to replace and maintain the batteries and the labor required to install the complex wired systems. This is particularly relevant to the installation of sensor networks in areas that are either inhospitable or difficult to reach. This includes safety monitoring devices, structure embedded microsensors, and medical implants. There are also environmental benefits associated with limiting the disposal of batteries. Energy harvesting devices therefore provide a battery-less solution by scavenging energy from ambient energy sources such as vibrations, heat, light, water, etc., and converting into a usable form, that is electrical power. When viewed on a large scale energy harvesting, this can be divided into two categories, that is macro and micro. Macro, in this the energy source are the renewable sources like solar, wind, etc., and the solution is the energy management solution, and the goal over here is to reduce the oil dependency. In the micro type, there are the energy sources are the small scale sources like vibration, motion, etc., heat, etc. And here the solution are the ultra low power solutions, and the goal is to drive low energy consuming devices. So piezoelectric crystals can be used to obtain a very small values of voltages and hence can drive low voltage devices. The piezoelectric energy harvesting comes under the category of micro scale energy harvesting scheme. Now let us discuss the innovative sources of vibration for piezoelectric energy harvesting. First is the power generating by sidewalk. The piezoelectric crystal arrays are laid underneath the pavements, sidewalks, and other high traffic areas like highways, speed breakers for maximum voltage generation. The voltage thus generated from the array can be used to charge the chargeable lithium batteries, capacitors, etc. These batteries can be used as per the requirement. Second is the power generator by the boots or the shoes. In US Defense Advanced Research Project Agency, DARPA initiated innovative project on energy harvesting which attempts to power the battlefield equipment by piezoelectric generators in soldiers' boots. However, these energy harvesting sources put an impact on the body. DARPA's effort to harness 1 to 2 watts from continuous shoe impact while walking were abandoned due to the discomfort from the additional energy expended by a person wearing the shoes. Next is by the gyms and the workplaces. Researchers are also working on the idea of utilizing the vibrations caused from the machines in the gym. At workplaces, while sitting on the chair, energy can be stored in the batteries by laying the piezoelectric crystals in the chair. Also, the studies are being carried out to utilize the vibrations in a vehicle like at clutches, gears, seats, shockups, footrests. Next is by the mobile keypad and keyboards. The piezoelectric crystals can be laid down under the keys of a mobile unit and keyboards. With the press of every key, the vibrations created can be used for piezoelectric crystal and hence can be used for charging purpose. Next is by using floor mats, tiles and carpets. A series of crystals can be laid below the floor mat, tiles, and carpets, which are frequently used at public places. Next, the final innovative technique is the people powered dance clubs. In Europe, certain nightclubs have already begun to power their nightclubs, strobes, and stereos by the use of piezoelectric crystals. The crystals are laid underneath the dance floor. When a bulk of people uses this dance floor, enormous amount of voltage is generated, which can be used to power the equipments of the nightclub. Now this shows a piezoelectric windmill for energy harvesting, where the energy harvesting is based on the direct piezoelectric effect. Output from a piezoelectric energy harvester. The output from a piezoelectric crystal is an alternating signal. In order to use this voltage for low power consuming electronic devices, it has to be first converted into a digital signal. This is done with the help of AC to DC converter as shown in this figure. This is followed by a capacitor or the storage capacitor, which gets charged by the rectifier up to a pre-decided voltage at which the switch closes and the capacitor discharges through the device. In this way, the energy can be stored in the capacitor and can be discharged when required. Energy harvesting circuit. Now, this shows the energy harvesting circuit where a DC to AC converter is used after the bridge rectifier stage, and it has been shown in this figure. The addition of the DC-DC converter, which is shown in this figure, has shown an improvement in energy harvesting by a factor of 7. A non-linear processing technique, that is synchronized switch harvesting on inductor SSHI, was also proposed in 2005 for harvesting the energy. It consists of a switching device in parallel with the piezoelectric element. The device is composed of a switch and an inductor connected in series. The switch is in open state except when the maximum displacement occurs in the transducer. At that instant, the switch is closed and the capacitance of the piezoelectric element and inductor together constitute an oscillator. The switch is kept closed until the voltage on the piezoelectric element has been reversed. Synchronized switch harvesting on inductor SSHI. So students, we have discussed this concept of SSHI, where a non-linear processing technique is the SSHI, and this is the circuit which shows the circuit arrangement of the output circuit having a very high energy harvesting capacity using the SSHI technique. And this technique has a very important application because of its very high energy harvesting capacity. So now let us discuss about the sensors. A piezoelectric sensor is a device that uses the principle of piezoelectricity to measure the changes in the surrounding and report those changes in the form of electrical signal. The principle of operation of piezoelectric sensor is that when stress is applied across the two opposing faces of the sensing element, a potential is developed across the two faces which can be tapped to generate the electrical signal. Piezoelectric sensors, they are very rugged in nature. That is, they have an extremely high natural frequency and an excellent linearity over a wide amplitude range. They have a very high DC output impedance, which can be modified as a voltage proportional source and filter network. The most common physical quantities that are measured by piezoelectric sensors are pressure and acceleration. So piezoelectric sensors, they are used in developing the combustion engine, high frequency sound in ultrasonic transducers, for medical imaging, industrial non-destructive testing, to detect the muscle movements in medical acceleromyography, etc. The piezoelectric sensor is kept in a casing on which a force is applied, or any other physical quantity which needs to be measured is applied, as shown in this figure. This applied force develops the stress according to the piezoelectric effect, eventually develops the electric field that can be tapped in the form of electrical signal, as shown by the movement of the needle of voltmeter, as shown in the figure. All these figures shows that the piezoelectric materials are being used in guitar pickups, bending sensors, and piezo disc. The most common physical quantities that are measured by piezoelectric sensors are pressure and acceleration. In the case of pressure sensors, a thin membrane and a massive base is used so that an applied pressure specifically loads the elements in one direction. So the figure shows the piezoelectric based pressure sensor. When the accelerometer, while for the accelerometers, a seismic mass is attached to the crystal elements, as shown in this figure. When the accelerometer experiences a motion, the invariant seismic mass loads the elements according to Newton's second law of motion. The main difference in the working principle between these two cases is the way they apply forces to the sensing elements. In a pressure sensor, a thin membrane transfers the force to the elements, while in accelerometers, an attached seismic mass applies the forces. The sensitivity of sensors is generally interfered by other physical properties. For example, pressure sensor shows false signal when they are exposed to vibrations. Due to this reason, modifications in the sensors are made to deliver accurate reading. As in the case of sophisticated pressure sensors, where acceleration, compression, compensation elements are used in addition to the pressure sensing elements. By carefully matching those elements, the acceleration signal released from the compensation element is subtracted from the combined signal of pressure and acceleration to derive the true pressure information. Now the below figure shows the piezoelectric based force sensor. So students, now let us discuss about the actuators. An actuator is a device that takes the electrical input from a sensor and converts it into a desired output. This output can be in the form of mechanical, electrical, magnetic, sound energy, etc., depending upon the required criteria. So, a piezoelectric actuator performs the same task, but the difference is in the fact that it uses the inverse piezoelectric effect to do the same. So, the actuator, it has lot of applications in the fields which has been categorized into three categories: positioners, motors and vibration suppressors. Two of the most popular actuator designs are the multi-layers and bimorphs. The multi-layer structure is characterized by quick response and high generative force, whereas bimorphs, they are categorized or characterized by larger displacements. Piezoelectric actuators, they are used in loudspeakers, tuning of laser frequencies to drive the ejection of ink from the inkjet print head towards the paper, to control it, the hydraulic valves act as small volume pumps or special purpose motors. This figure shows the principle of working of piezoelectric actuators. Now, as you can see, that when we apply a force, it deforms on the application of voltage. That is, when the electric voltage is applied across the faces of the actuator, it deforms, which produces the required mechanical actuation as depicted. Multi-layer piezoelectric actuator production. So this figure shows how a multi-layer actuator has been produced. That is, if we take a sheet and then place them layer wise, that is layering, and then molding and sintering, and after molding and sintering we bake and cuts, that is cutting and baking of all the insulating layers, and then the external electrode molding. Now another example of piezoelectric actuator used wireless remote, where it is clear from this picture that we twist the plate, that is move up and down the channels, then twisting the plate rapidly, that is switches the input, and bends the plate, turn up and down the volume. So bending the plate rapidly, holding one end of the plate and lightly shaking it, turns the power on and off. So these are the examples of piezoelectric actuators. So piezoelectric and electrostrictive devices have become key components in smart actuator systems such as precision positioners, miniature ultrasonic motors, and adaptive mechanical dampers. Application fields are classified into three categories: positioners, motors, and vibration suppressors. So, this figure shows the example of a piezoelectric positioning device, and on the right and on the left its principle of working. Now the next application of the piezoelectric actuators, they are used to drive the ejection of ink from inkjet print head towards the paper. So the below figure shows a piezoelectric fuel injector. The same principle as in the case of inkjet printers, it is used in fuel injection for automobile engines. The piezoelectric actuators, they are also used to control the hydraulic valves such as small volume pumps or special purpose motors. So all these figures shows the various examples of piezoelectric actuators. First shows the piezoelectric gas igniter. Second is the ultra compact piezoelectric actuator. And third is the ink injector. Now let us discuss about the piezoelectric motors. A piezoelectric motor, or we can say a piezo motor, is a type of electric which makes use of the converse piezoelectric effect, whereby the material produces acoustic or ultrasonic vibrations in order to produce a linear or rotary motion. Mostly these motors are used as ultrasonic motors. The basic construction of the most common ultrasonic motor includes, or it consists of a high frequency power supply, a vibrator, and a slider. The vibrator is composed of a piezoelectric driving component and an elastic vibratory part, and the slider is composed of an elastic moving and a friction coat. So the piezoelectric material having high mechanical quality factor is used in ultrasonic motors. Ultrasonic motors, they are driven in two ways: step drivers and direct drivers. Types of piezoelectric motors includes the traveling wave motor, the ink-worm motors, rectangular 4-quadrant motors, stepping piezo motors. Piezoelectric motors, they are used in manufacturing process, control, fiber optic positioning, camera autofocus, medical catheter placement, computer disk drivers, robotic positioning, pharmaceutical handlings, etc. So students, here we will be discussing the various types of piezoelectric motors. Now here the piezoelectric motors are of different types. Includes the traveling wave motor, ink-worm motors, rectangular 4-quadrant motors, stepping piezo motor. The following concept for designing the compact ultrasonic motors was proposed by Ukino. According to it, while designing an ultrasonic motor, the following things should be kept in mind. That is, simplification of the structure and the reduction in the number of components. Second, the use of simple polling configuration. And the third is the use of standing wave type for reducing the number of drive circuit components. So these are the different types of piezoelectric motors. First is the traveling wave ultrasonic motor, second is stepping rotary motor, and the third one is a linear motor. So students, let us now discuss the mechanism of stepper motor. First, at startup, all the four legs are elongated and bending, pressing against the armature of the motor. Second, one pair of leg retracts away from the armature and moves to the left, while the other pair of leg bends to the right, pushing the armature in that direction. The next is the leg pair that initially retracted now extends to push against the armature, while the first pair that pushed the armature to the right retracts. Now finally, the second pair bends to the right, continuing to push the armature in that direction while the original pair of legs now move to the left, preparing to start the walk cycle again. Now all these figures shows the various applications of piezoelectric motors, that is, they are used in stepping action as shown in figure 1, in figure 2 for camera autofocus, and in figure 3 for mirror mounts. Now let us discuss what are transducers. Piezoelectric materials like PVDF finds applications in electroacoustic and electromechanical transducers. Low frequency devices are mostly based on the excitation of flexural modes by the means of transverse piezoelectric effect, while in the upper ultrasonic range, the longitudinal piezoelectric effect is more advantageous. So this figure shows a schematic diagram of a piezoelectric transducer where the two electrodes have been applied on the adjacent faces of a piezoelectric crystal on which the voltage is being applied. Audio frequency transducer. Audio frequency transducers are based on transverse piezoelectric effect. If an electric signal is applied between the electrodes of the plain polymer film as shown in the figure A, the film vibrates in the transverse direction and the coupling to the surrounding medium is weak. Better coupling can be achieved by the arrangement shown in B of this figure, where the film has a cylindrical curvature and is clamped at its two straight edges. Due to the shape of the film, the transverse motion is now converted into a pulsating vibration which strongly couples to the surrounding medium. Ultrasonic and underwater transducers. Ultrasonic and underwater applications of the piezoelectric materials are based on the longitudinal piezoelectric effect. The effect of useful magnitude up to a frequency of at least 500 MHz at room temperature and 9 GHz at 1.5 Kelvin. There are several ways to generate and detect the ultrasonic waves using piezoelectric materials, but of the most simple design are the bulky wave transducers. As shown in this figure, a cylindrical PVDF sheet is properly mounted to generate the ultrasonic concentric waves, for example, in water. Similar transducers have been the subject of extensive theoretical and experimental studies with such quantities as insertion and dielectric losses investigated. Possible applications of such transducers are the measurement of ultra-low attenuation of liquids, the detection of particles or bubbles in flowing liquids, and non-destructive testing. So students, the next type of transducer which we are going to study is the electromechanical transducer. The electromechanical PVDF transducers, they are mostly low frequency devices and are therefore almost exclusively based on the transverse piezoelectric effect. The first device of this kind to be suggested were phonograph cartridges, utilizing a 1 cross 2 mm strips of PVDF as transducing applications or the elements. A high compliance vibrating system of high resonance frequency is obtained. The 45 kHz frequency response makes such cartridges suitable for the playback of CD4 records. An obvious application of PVDF is in contactless switches. These have potential use in telephone dials, typewriters, calculators, computer input terminals, etc. The operation of piezoelectric switches, such as the one shown in this figure, depends on the length expansion of the PVDF film due to the pressure created by a push button. So the maximum deflection is determined by the elastometer layer, but also may be controlled by a snap disk which guarantees tactile feedback and a more reproducible electrical output pulse. The basic two-film biomorph structure, also used in electroacoustic applications, produces often insufficient bending forces. Other applications of piezoelectricity includes the micromechanical systems or MEMS. MEMS are miniature smart systems consisting of multitude of mechanical devices that are integrated with large numbers of electrical elements on a substrate of silicon. The mechanical components are microsensors and microactuators. Microsensors, they collect the environmental information by measuring the mechanical, thermal, chemical, optical and magnetic phenomena. But the microelectronic components then process this sensory input and subsequently render the decisions that direct responses from the microactuator devices. The devices that perform such responses as positioning, moving, pumping, regulating and filtering. These actuating devices includes beams, pits, gears, motors and membranes, which are of microscopic dimensions on the order of microns in size. So piezoelectric materials, they have been successfully applied in a variety of MEMS applications, including acoustic emission sensors for structural health monitoring, vibration monitors, that is accelerometers, biosensors, precision positioners, peristaltic micropumps, and inkworm stepper motors. So these are the figures. First figure shows the SEM of the linear rack gear reduction drive MEMS. Second shows the basic structure of MEMS. And the third one shows the MEMS system chip. Piezoelectric transformers. When input and output terminals are fabricated on a piezo device and input-output voltage is changed through the vibration energy transfer, the device is called as piezoelectric transformer. Unlike a conventional transformer, which uses the magnetic coupling between the input and the output, the piezoelectric transformer uses the acoustic coupling. So where an input voltage is applied across a short length of a bar of piezoceramic material such as PZT, creating an alternating stress in the bar by the inverse piezoelectric effect and causing the whole bar to vibrate. The vibration frequency is chosen to be the resonant frequency of the block, typically in the 100 kHz to 1 MHz range. So this figure shows the schematic diagram of a piezo transformer. A higher output voltage is then generated across another section of the bar by the piezoelectric effect. By operating it above its resonant frequency, it can be made to appear as an inductive load, which is useful in circuits that require a controlled soft start. Piezoelectric transformers are some of the most compact high voltage sources, and they were used in color TVs in early 1970s because of their compact sizes in comparison with the conventional electromagnetic coil type transformers. Piezoelectric dampers. It is a device that is used to damp or suppress the excess vibrations produced in a mechanical device. When vibration is transmitted to the piezoelectric material, the vibration energy is converted into the electrical energy by the piezoelectric effect, and an AC voltage is generated. So if a proper resistor is connected, however, the energy converted into electricity is consumed in joules heating of the resistor, and the amount of energy converted back into the mechanical energy is reduced so that the vibration can be rapidly damped. Dampers are used in automobiles in order to damp the excessive vibrations produced in the engines. They also incorporated in smart building structures to damp. So these are the figures which shows the piezoelectric materials which are being used in the vibration controls as a damper. Piezoelectric vibrators. The piezoelectric vibrators uses the materials that are used in vibrational devices such as filters or oscillators. Two kinds of vibrational mode, that is the thickness mode and bending mode, are available in piezoelectric materials. So piezoelectric vibrators is a device that is used to produce the frequency vibrations using the principle of piezoelectricity. Mostly, they are used to produce the ultrasonic vibrations in ultrasound. For the vibrator applications, the piezoceramic having high mechanical quality factor QM rather than a large piezoelectric coefficient D are preferred. Piezoelectric vibrators are used in mobile phones and pagers in the form of soundless alarms for transmitting the one signal to the other, that is for the incoming calls. Piezoelectric resonator or filters. This figure shows piezoelectric resonator used as a diametric force sensor, and the right hand side figure shows a BAW filter. So piezoelectric resonator or a filter is a device that is used to filter the incoming wave and transmit the required frequency band. When a piezoelectric body vibrates at its resonant frequency, it absorbs considerably more energy than at other frequencies, resulting in a dramatic decrease in the impedance. This phenomenon enables the piezoelectric materials to be used as a wave filter. The bandwidth of a filter fabricated from a piezoelectric material is determined by the square of the coupling coefficient K. The piezoelectric materials can be found today in radio communications, telecommunications, signal generation, and GPS devices. Surface acoustic waves or a SAW device. A surface acoustic wave is a type of mechanical wave motion which travels along the surface of the material elastically and typically decays exponentially along the surface of the material and decays exponentially depth into the substrate. It is essentially the coupling between the longitudinal and shear waves. The energy carried by the SAW is confined near the surface. The energy interaction in SAW devices is basically in the form of acoustic and electric energy. The conversion process of energy is termed as transduction. A SAW device, whose basic design is shown in this figure, where there is an input transducer and there is an output transducer, consists of a minimum of two interdigital transducers, which are nothing but the input and the output one, using the principle of piezoelectricity to carry out this transduction. SAW is used in the front end and intermediate frequency filters, CATV and VCR components, synthesizers, analyzers, and navigators, as filters in mobile phones, and there are various other applications like for the LC filters, waveguide filters, as a sensor for sensing the chemical, optical, thermal, and biological molecules. So this figure shows the various modes of vibrations and their uses. Now when it is a flexural mode, then it can be used in the piezoelectric buzzer. When there is a length mode and the area expansion mode, it can be used in a ceramic filter and ceramic resonator in the kilohertz range. And when it has a thickness shear mode and thickness expansion mode, it can be used in the ceramic filter and ceramic resonator of megahertz range. And when they have the surface acoustic wave mode, they can be used in the SAW filters and SAW resonators. And when they are being used or they have the mode of BGS waves or SH waves, they can be used in HF trap, HF ceramic resonator, and HF ceramic filters. So students, let us summarize what we have learned in this module. First, we have discussed the large scale energy harvesting can be categorized into micro and macro energy harvesting depending on its goal. Second, the innovative sources of vibration for piezoelectric energy harvesting have been discussed. Third, description about the fetching of the output from a piezoelectric energy harvester is being discussed. Next, the sensors, that is the piezoelectric materials being used in guitar pickup, bending sensor and piezo discs and piezoelectric pressure sensor, accelerometer and force sensors, they have been discussed in detail. Next, we have also discussed about the actuators in terms of piezoelectric positioning device, piezoelectric fuel injector, piezoelectric gas igniter, ultra compact piezoelectric actuator, and ink injector. Next, we also discussed about the piezoelectric motors, basically the ultrasonic motors, rotary and linear motors, and traveling wave type motors. We also discussed about the transducers in terms of audio frequency, ultrasonic and underwater, and the electrochemical transducers. Lastly, the other applications of piezoelectric materials includes MEMS, piezoelectric transformers, piezoelectric dampers, vibrators, resonators, filters, and surface acoustic wave devices. They have been discussed in detail. Thank you.